Usually when we build a machine, there's this underlying expectation of just absolute precision.
Right. Like you want it to do exactly what you built it to do.
Exactly.
Mm.
Think of a classic mechanical watch. You pop the back open, you look at the gears, and you see exactly how the tiny brass teeth interlock.
Yeah, it's completely transparent.
Right. The watchmaker can point a pair of tweezers in there and tell you, this specific gear turns that specific gear, which clicks this spring, which moves the second hand exactly one tick.
Because it's completely deterministic. You apply a known physical force to the input, and you get an exact mechanically calculated output. I mean, it is a perfectly clean system of cause and effect.
It is. But then, and this is why we're here, you step into the world of modern artificial intelligence.
Oh yeah, that watch shatters pretty quickly.
It completely shatters. You look at neural networks, deep learning, large language models, and suddenly that beautiful, understandable mechanical watch is just gone. We're looking at a computational engine that it doesn't run on gears. It doesn't run on explicitly programmed if-then rules. It's a landscape that is, well, it's incredibly murky.
To most people, it is the absolute definition of a black box.
Yeah.
We've basically traded the comforting, tangible precision of interlocking brass gears for statistical probabilities and, massive matrices of numbers and multidimensional geometry.
And that's exactly why we are here today. If you've ever looked at a tool like ChatGPT or an image generator and wondered, how on earth does a computer actually teach itself to do this? We are going to pull back the curtain.
We are.
Our core mission for this deep dive is to completely demystify the mathematical engine of machine learning. Because everyone constantly talks about algorithms learning, but what does that actually mean on a mechanical level?
Right, how do they physically learn?
Wait, exactly. How do these models measure their own mistakes, navigate through a universe of data, and somehow, almost magically, get smarter over time?
Well, it often feels like pure magic, especially when you see the final results. But I promise you, and I promise our listener, there is no magic in the machine.
Zero magic.
Zero. It is just calculus, linear algebra, and statistics wrapped up in some very clever, very relentless optimization loops.
Okay, let's unpack this, because to get to the bottom of how this engine actually runs, we didn't just read a few blog posts, we went straight to the source code of the academic world.
We really dug in.
We did. Today we're digging into a notorious homework assignment from Carnegie Mellon University's Deep Learning course.
Oh, the infamous MyTorch project.
Yes, where students have to build a neural network from absolute scratch. We've also pulled lecture notes from the University of Toronto's machine learning program, some brilliant breakdowns by researcher Sebastian Roschka, a few incredibly dense mathematical papers on loss functions and sparse networks.
He's very dense.
And a groundbreaking paper from the Proceedings of the National Academy of Sciences that completely rewrote the rules of how models overfit.
It is a formidable stack of material, without a doubt.
It's huge.
But if we want to set the stage for you, the listener, we have to start by finding the common denominator. There is a beautiful, deeply logical thread running through every single one of these papers, lectures, and code repositories.
And what's that?
It's this. Machine learning is, at its absolute core, simply an exercise in minimizing wrongness.
I love framing it that way. Minimizing wrongness, not like maximizing rightness.
Well, mathematically speaking, there are often two sides of the same coin. But in practice, from a coding perspective, you always start by defining exactly what it means for your machine to fail.
Okay.
You create a mathematical formula, which we call a loss function, that basically spits out a number representing just how terrible the model's current guess is.
So a high number is bad.
Very bad. The entire training process is just the machine blindly feeling its way around a dark room, trying to make that wrongness number as close to zero as humanly possible.
So before the machine can learn anything at all, you have to explicitly teach it what failure looks like.
Precisely. And here is the catch that changes everything. How you mathematically define that concept of wrong completely dictates how the machine learns.
Interesting.
It dictates what features it pays attention to, what it ignores, and ultimately how it behaves when you release it into the real world.
That makes a ton of sense. If you define failure as being late, the machine will learn to rush, even if it breaks things. If you define failure as breaking things, it will move agonizingly slowly.
Exactly. The loss function is the ultimate incentive structure for the AI.
Let's start at the very beginning then.
Yeah.
Before a neural network can recognize a handwritten digit or, translate a novel from Mandarin to English or steer a self-driving car on a highway, it has to understand the absolute basics of drawing a line through a scatter plot of data points.
Right, the absolute basics.
Let's talk about the prediction game. Let's start with predicting continuous numbers, which, in statistics, we call regression.
Regression is the bedrock. If you look at Andrew W. Moore's slides from his neural networks course, which is one of our sources today, he lays this out with perfect clarity. Regression is the foundation of prediction.
Okay, lay it out first.
You, the human, have some inputs, which we universally call X, and you want the machine to predict an output, which we call Y. In the absolute simplest scenario, which is linear regression, you are assuming that the relationship between X and Y can be represented by a straight diagonal line.
Like drawing a line of best fit in high school science class?
Exactly like that. You are trying to find a weight, a multiplier called W, so that your prediction is just W times X.
Okay, let's put the listener in a real-world scenario to make this concrete. Imagine you are trying to sell your house. You want an algorithm to predict the fair market price. Your input, X, might just be the square footage of the house. And Y, the output, is the dollar price. The weight, W, that the machine is looking for is basically just the price per square foot.
That's a perfect example. If your house is 2,000 square feet and the algorithm guesses the weight should be $200 per square foot, it multiplies them and predicts a price of $400,000.
But real life is almost never one-dimensional. I mean, I can't just price a house solely on square footage. What about the number of bedrooms? What about the age of the roof? Or, how good the local schools are?
Right, and that is where we upgrade from simple linear regression to multivariate regression. Now, your input X is no longer a single number, it's a list of numbers.
Oh, okay.
In linear algebra, we call that a vector. It's a list of features: square footage, bedrooms, age, school rating. And correspondingly, your weight W becomes a weight vector.
So it's learning a bunch of multipliers at once.
Yes. The model has to learn a different multiplier for every single feature. Your final predicted price is the sum of each feature multiplied by its specific weight.
So it's like 200 times the square footage plus $50,000 for an extra bedroom minus $10,000 because the roof is 20 years old.
Exactly. In Andrew Moore's slides, he shows how this is computed using matrix notation. Instead of writing out a massive, tedious equation with dozens of plus signs, you just take the transpose of the weight vector and multiply it by the input vector.
Which sounds complicated, but
It's actually just an elegant mathematical shorthand that computers are incredibly fast at calculating.
okay, so the model makes a guess. Let's say it starts completely fresh with totally random weights. It looks at your house, multiplies the square footage by some random number, adds the bedrooms multiplied by another random number, and spits out a predicted price. Say $300,000.
Okay.
But you already sold the house, and the actual closing price was $400,000. The model's guess is wrong. But how does it mathematically measure that wrongness so it knows how to fix those weights for the next time?
This is where we introduce a massive concept in statistics called maximum likelihood estimation, or MLE. Finding the best weights isn't just about drawing a line that looks pretty on a graph. It is a formal statistical process of maximizing the likelihood that our specific mathematical model actually produced the real-world data we're observing.
Wait, I want to slow down here. Maximizing the likelihood. What does that actually mean? Are probability and likelihood the same thing?
No, and that's a really common confusion. Probability is when you know the rules of the game and you're trying to predict the data.
Like flipping a coin.
Exactly. If you know a coin is perfectly fair, you can calculate the probability of getting 5 heads in a row. Likelihood is the exact reverse.
How so?
You already have the data, you just flipped 5 heads in a row, and you are trying to guess the rules of the game. You are asking, given this data, what is the likelihood that the coin is weighted?
Okay, so in our housing example, we already have the real-world prices. The data is locked in. We are adjusting our model's weights to make it so that our model is the most likely explanation for why those houses sold at those specific prices.
Exactly. And statisticians proved something incredibly useful years ago. If we assume that the errors in our predictions follow a normal distribution,
Like a classic bell curve.
right, meaning most of the model's guesses will be pretty close, and absolutely wild, massive errors will be very rare. If we assume that, then maximizing the likelihood of our data is mathematically identical to minimizing the sum of the squared errors.
Okay, let me hold you to that. Why squared? Why not just take the raw difference? If the model guesses your house is worth $300,000 and it actually sold for $400,000, the error is exactly $100,000. Why does the math demand that I square that $100,000?
That question brings us to the first major loss function we need to examine today, which is detailed extensively in the ArcSiv paper on loss functions and metrics. It is called mean squared error, or MSE.
MSE, got it.
It is the absolute gold standard, the default metric for regression, often referred to in deep learning as the L2 loss. You take the difference between the prediction and the truth, you square that difference, you do it for every single house in your data set, and then you take the average.
But again, what is the mechanical purpose of the square?
There are two vital reasons. The first is about direction. Squaring the error makes every single penalty positive.
Okay.
Think about it. If the model overprices a house by $100,000, the raw error is positive $100,000. If it underprices the next house by $100,000, the raw error is negative $100,000. If you just added those raw errors together to see how the model was doing overall, the positive and negative would completely cancel each other out.
Oh, wow. The total error would equal 0.
Exactly.
The computer would look at a total error of 0 and say, awesome, I'm a genius. I have a perfect model, even though it missed every single house by $100,000.
Precisely. By squaring the differences, a negative error multiplied by a negative error becomes a positive number. Every mistake, whether it's an overestimate or an underestimate, accumulates as a positive penalty.
Okay, that makes sense. But couldn't you just use the absolute value to make them positive? Why square it?
That leads to the second and arguably more important reason, calculus.
Calculus.
The mean squared error function is mathematically smooth. If you graph y equals x squared, it forms a beautiful, continuous U-shaped bowl, a parabola. In the language of calculus, we say it is differentiable everywhere.
Meaning what, practically?
Meaning there are no sharp corners. At any given point on that bowl, you can easily calculate a tangent line, a slope. And if you know the slope, you know exactly which direction is downhill.
So the algorithm can just follow the slope down to the very bottom of the bowl.
Exactly, which is the global minimum, the point of least error. MSE gives the optimizer a very smooth, very predictable terrain to navigate.
Okay, I see the appeal. It's a nice, smooth bowl. But looking at the source text from the ArcSIF paper, I'm noticing a pretty massive flaw with MSE that we need to talk about.
Oh, it definitely has a flaw.
Right. If we square the errors, we aren't just making them positive. We are punishing large errors exponentially more severely than small ones.
We are. The penalty scales quadratically.
So imagine you're training this algorithm on a nice, normal suburban neighborhood. Most of the homes are modest, 3-bedroom places selling for around $300,000. The algorithm is drawing a nice regression line through them. But then right in the middle of this normal neighborhood, a tech billionaire buys a massive plot of land and builds a ridiculous $20 million mega mansion.
Okay, I see where this is going.
It's a total outlier. Now, our model looks at that mansion's square footage and, based on its current weight, predict a price of maybe $500,000. But the real price is $20 million. The raw error is $19.5 million.
And when you plug that into the mean squared error formula, you have to square 19.5 million.
That's a penalty of, what, nearly 400 trillion?
Roughly, yes.
That is a penalty so astronomically huge that it's going to completely freak out the algorithm. Won't the math panic? Won't the optimizer look at that massive 400 trillion penalty and violently tilt the entire regression line away from all the normal everyday houses just to try and appease that one single ridiculous outlier?
You have just independently discovered the exact reason why data scientists spend so much time arguing about loss functions. You are completely right.
Thank you.
Squared error is notoriously violently sensitive to outliers. Because of that squared term, a single massive anomaly in your dataset acts like a black hole. It has immense gravitational pull, it will drag the regression line toward itself, and in doing so, it will ruin the model's accuracy for the 99% of normal houses. The ArcSIF paper explicitly highlights this as MSE's greatest weakness.
So what do you do if you're the programmer? Do you just manually comb through thousands of rows of data and delete any mansions you find?
I mean, in a perfect world, you try to clean your data, yes, but data cleaning is never perfect. Sometimes you have millions of data points and manual review is impossible. And sometimes an outlier isn't a mistake. It's a valid data point that you actually want to keep, but you just don't want it dictating the entire model.
Right, it's real data.
So the algorithmic solution is to change your core definition of wrongness. You swap out the loss function. Instead of mean squared error, you use mean absolute error, or MAE.
Okay, let me guess. Instead of squaring the difference to make it positive, you just use the absolute value like we talked about earlier.
Exactly. This is also known as the L1 loss. If the model overprices a house by $100,000, the error is $100,000. If it underprices it by $100,000, the absolute value is still $100,000.
And the beauty of that is that a $200,000 error is penalized exactly twice as much as a $100,000 error, not 4 times as much. It's a linear proportional penalty.
Precisely. MAE treats all errors fairly. It doesn't give exponential weight to the extremes. Because of this, MAE is incredibly robust to outliers. It will look at that $20 million mega mansion, register the large absolute error, but it won't panic.
It won't get sucked into the black hole.
No, it will essentially ignore the mansion's gravitational pull and draw a regression line that fits the vast majority of the normal, modest homes much better. It focuses on the median rather than being skewed by the extremes.
That sounds vastly superior for real-world messy data. So why isn't MAE the default? Why is everyone still using the squared error bowl?
Because in machine learning, there is always a trade-off. Remember how we praised MSE for being a beautiful, smooth, differentiable bowl?
Yeah.
MAE is not a bowl. If you graph the absolute value function on a chart, it looks like a giant capital letter V. The sides are perfectly straight, diagonal lines, and they meet at a sharp, jagged point at the very bottom, exactly where the error is 0.
And earlier you said the calculus relies on smooth curves?
Calculus absolutely hates sharp points. At the very bottom of that V, the mathematical derivative, the slope, is suddenly undefined. It breaks the calculus.
Why does that matter practically, though? If the algorithm is rolling down the side of the V, doesn't it just hit the bottom and stop?
No, because it takes steps based on the slope. On the smooth bowl of MSE, as you get closer to the bottom, the bowl flattens out. The slope gets gentler. So the algorithm naturally takes smaller and smaller steps, gently easing into the perfect minimum.
Oh, I see.
But on the V shape of MAE, the slope is a constant steep diagonal all the way down to the microsecond before you hit the bottom. The algorithm doesn't slow down. It takes a massive step, overshoots the 0 point, climbs up the other side of the V, calculates the steep slope there, turns around, and takes another massive step.
It just bounces.
It ends up violently bouncing back and forth across the minimum, never actually settling into the perfect answer.
That is fascinating. It's a true dilemma. MSE is incredibly easy for the computer to optimize because of the smooth bowl, but it is completely brittle and easily distracted by outliers. MAE is tough, robust, and ignores outliers. But it is mathematically annoying to optimize because it bounces around that sharp corner.
Which is exactly why mathematical researchers had to invent hybrids. The ArcSiv paper dedicates a section to the Huber loss. Think of it as a Frankenstein function.
A Frankenstein function?
Yeah, the creators basically chopped up the two graphs and glued them together.
How does that work?
It acts like MSE when the errors are small. So the very bottom of the loss landscape, it has that nice, smooth, curved, differentiable bowl. The algorithm can gently settle into the minimum without bouncing. But once the errors cross a certain threshold, once they get too large, the function transitions into acting like MAE. It becomes a straight, linear slope.
So if a massive outlier appears,
it doesn't incur that exponential quadratic penalty.
It's literally the best of both worlds.
Yeah.
You get the stability of the bowl and the robustness of the straight walls.
Exactly. And just to round out our discussion on regression metrics, the sources mention a few specialized ones. There is Poisson loss, which is critical when your data isn't a continuous measurement like money, but rather a discrete count.
Like counting the number of customers walking into a coffee shop per hour.
Right. You can have 0 customers, or 5 or 20, but you can never have negative 3.4 customers.
That's impossible.
But standard regression models don't know that. They might happily predict negative customers if the features push them that way. Poisson loss mathematically constrains the model to understand the nature of count data, heavily penalizing any attempt to predict impossible negative numbers.
And I also saw R² mentioned in the papers. Is that a loss function?
Good catch. No, R² is not a loss function. The algorithm does not use it to update its weights during training. It is an evaluation metric for the humans.
Okay, so just for us to read.
Exactly. After the model is trained, R² tells you the proportion of the variance in your data that your model actually explains. An R² of 1.0 means your model perfectly predicts every single point. An R² of 0 means your model is completely useless. It's essentially just predicting the average house price for every single house, ignoring the square footage and bedrooms entirely. It's a reality check for the data scientist.
Okay, so we have deeply established how a machine learns to predict a continuous number, like a house price or a temperature. We define the loss, the wrongness. We measure it using a bowl or a V shape, and we adjust the weights to lower that number. But I want to pivot our deep dive now. What if you don't want a number? What if you want your model to categorize things?
Classification.
Right. If I'm building an app, I don't want the neural network to predict the exact wavelength of light bouncing off a photograph. I want the network to look at the photo and tell me definitively if it is a picture of a cat, a dog, or a car. You can't just draw a straight regression line through discrete categories. Car is not mathematically greater than dog. They aren't points on a number line.
Exactly. If you tried to use linear regression to classify a cat versus a dog, the straight line would just shoot off into positive and negative infinity. A prediction of 4,000 doesn't mean anything in the context of a cat. We need to completely bound our predictions. We need to squash them.
Squash them. I like that.
And this brings us perfectly into the realm of categorization, transitioning from logistic regression to softmax. For this, we are going to lean heavily on the incredibly clear lecture notes provided by Sebastian Raschke.
Let's start with the simplest version of categorization. Binary. Yes or no, true or false, spam or not spam. Raschke makes a really provocative statement in his notes. He says that logistic regression isn't actually a regression algorithm at all. It is a classification algorithm, and it can be viewed as a single-layer artificial neural network, the absolute simplest neural network possible.
It is a profound way to look at it, and mathematically it is entirely accurate. Imagine you are building that spam filter. You still have inputs, maybe the frequency of the word free, the number of exclamation points, whether the sender is in your contacts. You still multiply those inputs by weights, and you add them all up, exactly like we did for the house prices.
So you still calculate a raw number.
Yes. That raw sum of all the weighted inputs is called the net input. In deep learning jargon, we call it the logits. Now, in our previous housing example, we just output that logit directly as the price. But here, that raw logit could be negative 1,000,000 or positive 10,000. To make it useful for classification, you take that logit and you pass it through an activation function.
And for logistic regression, that specific activation function is called the logistic sigmoid function.
Correct. The sigmoid function is a mathematical marvel. If you graph it, it has this beautiful, smooth S shape. It acts like an absolute mathematical trash compactor.
A trash compactor.
Yeah, it doesn't matter how infinitely huge or infinitely negative your raw logit number is. You feed it into the sigmoid function, and the math squishes it into a value strictly bounded between 0 and 1.
Which is incredibly convenient because as humans, we universally interpret any number between 0 and 1 as a probability.
Exactly. If the raw math outputs a massive positive number, the sigmoid squishes it to something like 0.99. We look at that and say, the model is 99% confident this email is spam. If the raw math is a huge negative number, it gets squished to 0.01, 1% confident. And if the raw math is exactly 0, it gets squished to 0.5. The model is essentially shrugging its shoulders, saying it's a coin toss.
This is a brilliant mechanism. But it raises a huge problem for our loss function. We squish the output. We can't really use our old friend mean squared error to measure the wrongness here, can we?
We absolutely cannot.
Let me guess. It breaks the calculus again.
It completely destroys the loss surface. If you take the sigmoid function, that complex S-curve, and you plug it directly into the squared error formula, the resulting landscape of the loss function is no longer a nice, smooth, predictable convex bowl. It becomes wavy, distorted, and highly non-convex. It becomes a landscape filled with hills and valleys, full of what we call local minima.
Local minima. Explain that for the listener.
Imagine you are blindfolded, trying to walk to the lowest point in a valley. If the valley is a perfect bowl, you just step downhill until you hit the center. But if the valley is wavy and covered in craters, you might step downhill and find yourself at the bottom of a small, shallow crater halfway up the mountainside.
And because you're blindfolded.
Because everywhere around you goes up, you think you found the bottom. The algorithm stops learning. It gets trapped in that local minimum, completely oblivious to the fact that the true deep valley, the global minimum, is miles away. Using MSE on sigmoid outputs creates a landscape made entirely of deceptive craters.
So if MSE is off the table, we need an entirely new definition of wrongness for dealing with probabilities.
And that new definition is called negative log likelihood, which is also commonly referred to in deep learning as cross-entropy loss.
Cross-entropy loss.
Right. Let's trace it back to our earlier concept, maximum likelihood estimation. When we're classifying spam, we want to maximize the probability that our model outputs the correct label. If the true label of the email is 1, meaning it is definitely spam, we want the model's output probability to be as incredibly close to 1.0 as possible.
Right. If the email is spam and the model outputs 0.99, it is doing a fantastic job. The error should be tiny.
But here's where we hit a massive hardware limitation with computers. When you want to evaluate how good your model is doing across an entire data set of, say, 10,000 emails, statistics requires you to multiply the probabilities of all those independent events together to get the joint probability.
Wait, I remember this from high school math. If I flip 2 coins, the probability of getting 2 heads is 0.5 times 0.5, which is 0.25.
Exactly. Now imagine you are multiplying 0.9 times 0.9 times 0.8 times 0.99, and you do that 10,000 times in a row.
Every time you multiply 2 numbers smaller than 1, the result gets even smaller. If I multiply 10,000 probabilities together, I'm going to get a number with thousands of zeros after the decimal point.
And that is the fatal problem. The silicon chips in our computers only allocate a certain number of bits to store a number. When a number gets that microscopically small, the computer physically runs out of memory to track all those zeros. It just throws its hands up and rounds the number down to absolute zero.
And the math crashes.
It's called numerical underflow. It breaks the entire optimization process. So computer scientists use a brilliant mathematical workaround. Instead of multiplying the raw probabilities, we take the natural logarithm of every single probability first. Because of the mathematical rules of logarithms, multiplying probabilities turns into adding log probabilities.
Addition.
Yes. Addition doesn't cause underflow. It completely saves the computer's memory.
I want to make sure I grasp this, because in the outline I was given, it specifically warned me not to call this magic. There is a real mechanism here. A logarithm basically asks, to what power do I have to raise my base number to get this value? It compresses astronomical scales into manageable linear steps.
That is exactly right. It compresses the scale so the computer can handle it.
But the metric is called negative log likelihood. Where does the negative come from?
Well, think about the probability values. They are strictly between 0 and 1. If you take the logarithm of any fraction between 0 and 1, the result is always a negative number. The log of 0.1 is roughly negative 2.3. But remember our overarching theme. Machine learning algorithms are designed to minimize a loss function.
They want to walk down the hill.
Right. They don't know how to maximize a negative score. So to make the math work with our standard gradient descent algorithms, we just flip the sign. We slap a negative on the front. Maximizing the log likelihood is mathematically identical to minimizing the negative log likelihood.
It's a brilliant hack. We compress the numbers so the computer doesn't crash, and we flip the sign so we can use the exact same downhill walking algorithms we used for the housing prices without having to rewrite the core optimization code.
It is incredibly elegant.
Okay, but logistic regression has a severe limitation. It is strictly for binary problems. Spam or not spam. Tumor or no tumor. What if I have 10 different categories? What if I'm looking at the famous MNIST dataset, which Roshka mentions heavily in his notes? It's a dataset of 60,000 images of handwritten digits, numbers 0 through 9. Logistic regression cannot handle 10 simultaneous classes.
No, it can't. You would have to train 10 separate binary models, which is inefficient and clunky. That is where we introduce the softmax function.
Softmax.
Softmax is the multi-class, bigger sibling of logistic regression. It generalizes the math so that you can classify an input into any number of mutually exclusive categories, 3, 10, or 1,000.
I love explaining softmax to people, and I always use the analogy of baking a pie. Let's say you feed a photograph into your network, and you want it to classify the image as a cat, a dog, or a car. The neural network's internal layers crunch the numbers and compute raw logit scores for all 3 categories. Let's say the raw math spits out a score of 5 for cat, a 2 for dog, and a negative 3 for car. Those are just arbitrary numbers. Softmax takes those raw, unconstrained scores and it bakes them into a single, cohesive pie of probability.
And what is the defining unbreakable rule of a probability distribution?
That all the probabilities must add up to exactly 1.0 or 100%.
Exactly.
So softmax divides the pie. Based on those raw scores, maybe it hands out 80% of the pie to the cat category, 15% to dog, and 5% to car. But here is the critical part, the mechanism that makes it soft but powerful. Because there is only one pie, the classes are inherently forced to compete against each other.
Right, it's a zero-sum game.
Yes. If the model runs another layer of processing and suddenly decides the probability of cat needs to increase from 80% to 95%, it cannot just invent more pie from thin air. The probabilities of dog and car must be mathematically squished down to 4% and 1% to make room.
That competitive aspect is vital for classification. It forces the model to actually make a decision rather than just saying, I'm highly confident it's a cat, but I'm also highly confident it's a car.
Which wouldn't make sense.
Right. The specific math behind softmax involves taking the exponential function to the power of the raw logit, which forces every number to be positive. Then, it divides each of those exponentials by the sum of all the exponentials combined. This mechanism radically highlights the largest value while aggressively suppressing the smaller ones. That's why it's called softmax. It's a softer, continuous, differentiable version of a hard maximum function.
Now, conceptually, that is beautiful. But if we dive into deep learning textbook sources, the D2L materials, and the PyTorch implementation cheat sheet Rashka provided, there is a really interesting, incredibly frustrating practical reality here. Students, and even seasoned developers, get insanely confused by how software frameworks like PyTorch actually handle these loss functions in the code.
Oh, the loss input confusion. It is an absolute rite of passage for every single machine learning engineer.
Yeah.
PyTorch, which is the dominant programming framework, offers several different functions that sound like they do the exact same thing. But if you use the wrong one, your model completely fails to learn, and the error messages are often deeply unhelpful.
Exactly. Rashka outlines the trap perfectly. For binary classification, PyTorch gives you binary cross-entropy. If you use this function, the code expects that you, the programmer, have already passed your raw numbers through a sigmoid function yourself, so the inputs are strictly between 0 and 1. But right next to it in the library is binary cross-entropy with watchets. This function expects the raw, unsquished, unactivated numbers. It performs the sigmoid step for you, hidden internally.
And the confusion multiplies when you move to multi-class problems. You have cross-entropy, which takes the raw logis and performs both the log and the softmax operations internally for you. And then you have Anawal's negative log likelihood loss, which expects you to have already explicitly performed the log softmax step in your own code.
It begs a question. Why make the API so confusing? Why have dedicated functions that hide the activation step inside the loss calculation? Why not just let the programmer do the activation and let the loss function just calculate the loss?
It all comes back to the physical limitations of computers. Numerical stability. Let's say you decide to calculate the softmax probabilities explicitly in your code, and then you pass those probabilities to a separate log function to calculate the loss. Because of rounding errors with floating point math, your explicit softmax might spit out a probability of absolute literal 0 for a class it thinks is highly unlikely.
And what happens when you hand a 0 to a natural logarithm function?
The logarithm of 0 is mathematically negative infinity. Your Python code will instantly crash. It will throw a nan error, not a number, and your entire training run, which might have been going for days, is ruined.
That's devastating.
It is. By combining the softmax operation and the log operation into a single fused internal PyTorch function, the developers of PyTorch can use algebraic tricks under the hood to cancel out the dangerous terms before they are ever explicitly calculated by the processor. It keeps the calculations perfectly mathematically stable.
That is the ultimate hidden hero of deep learning frameworks. We sit here and theorize about the beautiful math on a whiteboard, but inside a silicon chip, you need these hardcore engineering tricks to keep the math from literally exploding into infinity.
And understanding that bridge between theory and code sets the stage perfectly for our next leap. We now have our model, whether it's predicting a continuous regression line or dividing up a softmax probability pie, and we have our measure of error, our computationally stable loss function. The board is set.
But how does the model move?
Exactly. How does it look at a negative log likelihood of 0.8 and decide, I need to increase weight number 47 by exactly 0.02? How does it physically learn?
Which takes us to the absolute core of the engine. Optimization. Navigating the loss surface. We keep talking about walking down a hill or finding the minimum. I want to really expand on this visualization. If you look at the YouTube transcript we pulled from Math Unlocked with Katrina, she describes the loss function not as a simple curved bowl, but as a highly irregular, multidimensional, nonlinear mountain range.
It is the most accurate visualization you can have, but it is hard for the human brain to grasp. We live in 3 dimensions. We can imagine a 3D mountain range with latitude, longitude, and altitude. But in a neural network, every single weight is a different dimension.
Wow.
If you have a modern language model with 1 billion parameters, you're trying to navigate a space with 1 billion dimensions.
My brain just short circuits trying to picture that.
Everyone's does. But conceptually, the altitude in this incomprehensible hyperdimensional landscape is the loss, the total error. Your Model starts with random weights. That means it is essentially dropped by parachute onto some random high-altitude peak in this billion-dimensional mountain range. The error is huge. The altitude is high. The overarching goal of the entire learning process is to find a path down to the lowest possible valley, the global minimum, where the error is closest to zero.
But the model doesn't have a drone. It doesn't have a satellite map. It is blindfolded in the dark. It can only feel the ground directly beneath its feet. So in a billion dimensions, how does it know which way is down?
This is where we rely on one of the most powerful tools in mathematics, the Taylor series approximation. The video transcript explains this wonderfully. A real-world loss surface of a neural network is insanely complex. It is a massive, interwoven equation of millions of variables. It might not even have a closed-form mathematical solution that you can just solve with algebra.
So we can't solve it.
We cannot solve the entire mountain range at once. It is computationally impossible for any computer on Earth.
So if we can't solve the mountain, what do?
We reframe the problem. Instead of trying to understand the whole mountain, we use a Taylor series to create a simplified local approximation of the ground right under our feet. We take a massively complex, unsolvable function and turn it into a simple, solvable polynomial equation that is only accurate for a few inches around where we are currently standing.
Okay, let me try to translate that. A first-order Taylor approximation basically means we pretend that the complex, bumpy ground beneath us is just a perfectly flat, tilted plane. We use calculus to calculate the exact slope of that flat plane, and we take one small step downhill in the steepest direction. And that is the essence of gradient descent, right?
Exactly. You calculate the slope, take a step, recalculate the new slope, take another step. Now, a second-order Taylor approximation is slightly more advanced. Instead of a flat plane, we pretend the ground beneath us is a quadratic polynomial, a curve, like a parabola. We look at not just the slope, but the curvature of the ground. Is the slope getting steeper, or is it flattening out?
Why is knowing the curvature helpful?
Because it lets you anticipate the terrain. If you know the ground is flattening out, you know you are approaching the bottom of the valley, so you can adjust your step size perfectly. This leads to more advanced optimization algorithms like Newton's method, which can converge on the true minimum much faster than simple gradient descent.
Sounds great.
But there is a massive catch.
What's it?
Computing the curvature, the second derivative, for millions or billions of parameters, requires creating a matrix called a Hessian. The size of that matrix is the number of parameters squared. If you have 1,000,000 parameters, the Hessian has 1,000,000,000,000 entries. It requires so much computational power and memory that it is entirely unfeasible for deep learning. So in practice, we largely ignore the curvature and stick to first-order approximations. Simple, reliable gradient descent.
Okay, so we're using first-order slopes. But let's go back to my previous confusion. We aren't just walking north or south on a 3D mountain. We have 1,000,000 dimensions. There are 1,000,000 different directions to step. How does the computer figure out the slope for every single weight? Doesn't the math just become an entangled mess?
It would if it weren't for the Jacobian matrix and partial derivatives. The machinelearningmastery.com source we reviewed breaks this down very gently. To figure out the slope in a multidimensional space, you use a partial derivative. And a partial derivative is essentially an isolation tool.
I love analogies, so I'm going to try one here. Let's say you are the coach of an American football team. The team runs a play, and it is a total disaster. They lose 10 yards. The coach is furious, and he wants to know exactly who is to blame.
Naturally.
And if he just looks at the whole chaotic play, it's a mess of moving parts.
Right.
But what if he had a magic simulator? What if he could freeze time, keep 10 of the players absolutely frozen in their exact positions, and only let the quarterback move? He runs the simulation, and he sees how the quarterback's isolated movement changed the outcome. Then he freezes the quarterback, unfreezes the left tackle, and runs it again.
That is a brilliant analogy. That is exactly what a partial derivative does mathematically. It asks, if I hold every single weight in this entire neural network completely frozen, and I only tweak this one specific weight by a tiny fraction, how much does the total error change? It isolates the blame. It figures out exactly how much of the wrongness is the fault of weight number 47.
So it does that freezing simulation for every single player, every single weight.
Yes. And it stores all those individual blame scores in a giant grid. That grid is the Jacobian matrix. It is basically the coach's clipboard, containing a specific grade for how every single parameter contributed to the error.
Got it.
Once we have the Jacobian, we know the exact slope for every single dimension. We multiply those slopes by a small number called the learning rate, which controls how big of a step we take, so we don't accidentally leap over the valley entirely. And we update all the weights simultaneously. Then we calculate the loss again, compute a new Jacobian, and take another step, iteration by iteration.
Okay, conceptually that makes total sense. But mechanically, how do we actually compute those partial derivatives in a deep network? Because a deep network has multiple layers. The input image goes into a hidden layer, which crunches it and passes it to another hidden layer, which passes it to another, which finally produces a prediction.
Right.
The error is only measured at the very, very end of the line. How does a weight in the very first layer, near the input, know what its partial derivative is? It has no direct connection to the final error.
That is the multi-million-dollar question, and the answer is the most important algorithm in the history of artificial intelligence: backpropagation. The MIT Brain and Cognitive Sciences paper outlines the intense math for this, and it all relies on a foundational concept from calculus called the chain rule.
Walk me through the chain rule like a detective story.
Okay. The crime happens at the very end of the network. The output layer makes a prediction, and it's wrong. We calculate the loss. We know exactly how much the final output nodes are to blame. Now, the output layer acts as the detective. It looks at the layer immediately before it, the last hidden layer, and says, I was wrong because of the signals you sent me. Based on the weights connecting us, here's exactly how much you need to change your signals for next time.
So the error signal is passed backward.
Yes. Now, that hidden layer has its own blame scores. It uses its own weights to translate that message, turns to the hidden layer before it and says, based on what the output told me, here is how much you are to blame and how much you need to change. The chain rule allows us to multiply these derivatives together, chaining them backward through the network, layer by layer, transmitting the error signal from the output all the way back to the very first input layer.
So every single weight eventually finds out exactly how its tiny tweak cascaded through all the subsequent layers to cause the final error?
Exactly. It's a reverse cascade of accountability.
I have to say, tracking thousands of moving parts, multiplying massive matrices together, reversing the flow of calculus, this sounds like an absolute nightmare to program by hand.
Oh, it is a profound nightmare. And that brings us to the Carnegie Mellon University My Torch homework assignment. This assignment is legendary. It is an infamous, grueling rite of passage for computer science students at CMU. Because out in the real world, in a corporate job, you use PyTorch or TensorFlow. Those frameworks have a feature called autograd automatic differentiation. They track the computational graph and calculate the entire backward pass for you invisibly in the background. You literally just type loss.backward, and it does the calculus.
But in the CMU assignment, I'm assuming autograd is strictly forbidden.
It is banned. The assignment forces the students to build a multi-layer perceptron and MLP entirely from scratch. They have to code the linear layers, the sigmoid activation functions, the mean squared error, the cross-entropy loss, and most brutally, they have to manually write out the matrix multiplication code using raw NumPy arrays to perform the forward pass, and then hand code the reverse chain rule math for the backward pass.
I read through the assignment brief in our sources. The professors put a huge warning box in the text. It explicitly says, we don't want you to translate math equations to codes without understanding them. And it heavily warns them about dimension mismatches.
Yes, the dimension mismatches are the terror of the backward pass. When you are multiplying matrices, the inner dimensions have to align perfectly. If you have a batch of inputs, say n images, and each image has c features, your matrix is n rows by c columns. If your weight matrix is c rows by d columns, you can multiply them to get an n by d output. But during backpropagation, you have to compute the gradients of the loss with respect to the weights, which we call dw, and the gradients with respect to the inputs, dx.
And doing that requires transposing the matrices, flipping the rows and columns.
Exactly. And if you transpose the wrong matrix or multiply them in the wrong order, the dimensions clash. The code doesn't just give you a wrong mathematical answer, it completely crashes with the dimension mismatch error. The students have to meticulously track the exact shape of every single tensor on a whiteboard as it flows forward and backward through the network. It forces them into the absolute trenches of linear algebra.
So what does this all mean? It sounds like a brutal way to spend a weekend debugging a transposed matrix at 3 a.m., but I imagine it produces a profound, unshakable level of understanding. When you build the calculus engine from absolute scratch in NumPy, the illusion disappears. You realize there is no magic AI brain in the box.
Exactly. It demystifies the entire field. It proves that underneath all the sci-fi portrayals and media hype, it is just an algorithm iteratively calculating partial derivatives and blindly taking steps down a mathematical hill. It is staggeringly beautiful in its complexity, but it is fundamentally, rigidly mechanical.
Mechanical, yes. But let's go back to the terrain. The landscape is treacherous.
Mhm.
Earlier, you talked about local minima, those craters on the side of the mountain. If the algorithm only looks at the slope right under its feet and it steps into a crater, every direction looks like it goes up. The slope is 0. The algorithm says, great, I'm at the bottom of the world. But the true global minimum is 10 miles away. Won't simple gradient descent just get permanently trapped in that ditch?
It absolutely will. Standard vanilla gradient descent is incredibly vulnerable to local minima, saddle points, and flat plateaus. It is a massive problem. But the CMU homework introduces the students to the primary solution used in modern AI, stochastic gradient descent, or SGD, with momentum.
Momentum. That sounds like physics, not calculus.
It is directly inspired by physics. In standard SGD, the algorithm has zero memory. It is purely reactive. It looks at the slope at the current exact microsecond, takes a step, and forgets everything that just happened. If the slope hits 0, like at the bottom of a small ditch, it stops dead. It has no inertia.
But with momentum, we add a velocity term to the math.
Yes. We force the optimizer to remember the direction and the speed it was traveling in the previous steps. We add a fraction of the previous step's update to the current step's update.
So imagine a heavy boulder rolling down the mountain. It has been rolling down a steep, consistent hill for a while, building up massive speed and kinetic energy. Suddenly, it hits a small, shallow ditch. Because it has momentum, it doesn't just stop at the bottom of the ditch. It has enough kinetic energy to literally roll up the other side, blast right out of the crater, and continue its journey down the larger mountain.
That is exactly how it works. In the CMU code, there is a parameter called m that controls this momentum rate, acting like a friction coefficient. It allows the optimizer to barrel through small, deceptive dips in the loss surface and cruise over flat plateaus where standard descent would stall. It might oscillate and swing back and forth a bit when it finally reaches the true valley, but it prevents the model from dying in a shallow crater. It is a simple, elegant hack that makes deep learning possible.
Okay, so let's say our momentum carried us through. We successfully trained our model, we navigated the billion-dimensional mountain, avoided the craters, and our model is now resting perfectly at the absolute bottom of the deepest valley. The training error is basically 0. The model correctly identifies every single image in our data set. We popped the champagne right. We've created the perfect AI.
I would strongly advise against opening the champagne. In fact, if your neural network has a training error of absolute 0, you should probably be terrified.
Terrified? Why? Isn't 0 error the entire point of everything we just talked about?
It is the point of the optimization engine, yes, but it is not the goal of machine learning. If your training error is 0, you have likely fallen victim to the greatest enemy in all of data science.
Overfitting.
Overfitting. Let's unpack that. As neural networks get deeper, adding more layers and hundreds of millions of parameters, they gain an unfathomable amount of computational capacity. They become so incredibly flexible and complex that they stop learning the underlying patterns of the data. Instead, they just use their massive memory banks to explicitly memorize the training data set perfectly.
Memorize it.
And when I say perfectly, I mean they memorize the true signal, but they also memorize all the random noise, the sensor static, the typos, and the weird outliers.
Ah. It's like a student who gets a copy of a practice test before the SATs. They don't bother learning the concepts of algebra or grammar. They just ruthlessly memorize the exact answers to those specific 50 questions. They score a 100% on the practice test 0 training error. But when you put them in the real exam room with questions they have never seen before, they completely fail.
That is the perfect analogy. When you deploy an overfitted, memorized model into the real world, testing it on data it has never seen before, it fails miserably. The test error is huge, even though the training error was 0. It has 0 ability to generalize. And this brings us to a critical pivot in our discussion. We need to discipline the model. We need to physically restrain its capacity so it is forced to learn patterns instead of just memorizing the answer key.
And one of the most fascinating ways to impose this discipline is detailed in the paper on sparse deep learning by Shen, Wang, Xu, and Yan. They propose using L1 regularization. Now, we mentioned L1 way back at the beginning of this conversation as mean absolute error for the loss function. But here, they aren't using it to measure the final output error. They're using it as a penalty term added directly to the weights themselves.
Yes, this is a crucial distinction. The goal of this specific paper is to create what they call sparse neural networks. A standard, dense neural network uses every single one of its millions of weights. Every neuron is connected to every other neuron, and every pathway is active, even if it's only contributing a tiny fraction to the final answer.
But a sparse network is different.
A sparse network is one where a massive percentage of those weights are explicitly forced to equal exactly zero. Mathematically, they are turned off, the neural pathways are severed, the network goes from a dense, tangled web to a very minimal, streamlined skeleton.
Why is that desirable? Is it just about saving hard drive space?
Saving memory footprint and speeding up the computation is a huge part of it, absolutely. If you want to run a powerful AI locally on a smartphone or a smartwatch, you can't have it calculating a billion dense weights. It will drain the battery in 5 minutes. But even beyond hardware constraints, forcing the network to be sparse acts as a brutally effective regularizer. By literally deleting millions of parameters, you are stripping away the network's excess capacity. You are removing its ability to memorize the noise, forcing it to rely only on the most critical, robust pathways to make its predictions.
Okay, I understand the why, but I really need you to explain the how. The mathematical insight in this paper dives into the Bayesian statistical viewpoint of why L1 regularization physically creates exact zeros in the network. The math relies on something called a MAP estimate and a Laplace prior. I'm not going to lie, when I read those words, my brain starts to shut down. What does that actually mean mechanically?
It is heavy math, but let's ground it. In Bayesian statistics, a prior is simply your mathematical belief about the state of the world before you even look at the data. When we train a normal neural network with standard L2 regularization, also called weight decay, we are implicitly assuming a Gaussian prior.
A Gaussian prior, like a normal bell curve.
Exactly. We are telling the model, before we start, I believe that most of the weights should be clustered around zero, but a few can be larger. Think of the Gaussian prior like a smooth, shallow bowl. As the optimizer tries to minimize the weights, it rolls the marble down the side of the bowl towards zero. But because the bottom of the bowl is smooth and relatively flat, the marble might stop rolling at 0.0003 or 0.0001.
It pulls them very close to zero, making them tiny, but it rarely forces them to be exactly zero. The weights are shrunk, but they aren't dead.
Precisely. But if we change our core mathematical assumption, if we swap out the Gaussian prior for a Laplace prior, the physical geometry of the math changes completely. A Laplace distribution does not look like a smooth bowl. It looks like a steep, sharp, pointed tent. It has a jagged peak exactly at zero. It looks incredibly similar to the V-shape of the mean absolute error we discussed earlier.
So how does that force a zero?
Let's use a physical analogy. Imagine you have a rubber band attached to a weight. In L2 regularization, you are pulling that rubber band along a smooth, curved surface. It comes to rest near the bottom, but friction might stop it a little off-center. In L1 regularization with a Laplace prior, you are pulling that rubber band into a sharp, rigid V-shaped trough. Because of the steep, straight walls and the sharp point at the bottom, there is only one stable resting place for the physical tension. Exactly, precisely at the dead center of the crease.
Wow.
The optimization process, mathematically solving the maximum a posteriori or MAP estimate, essentially yanks the weights down the steep walls of the Laplace distribution until they lock into that sharp point. It forces a large number of the weights to become exactly zero.
I love that physical visualization. The V-shaped trough forces the issue. I also like to think of L1 regularization as the Marie Kondo of machine learning. Yeah. The neural network, left to its own devices, is an absolute hoarder. It wants to keep every single weight, every tiny useless neural pathway, just in case it might be useful for memorizing one specific, noisy data point.
Yeah.
L2 regularization is like asking the hoarder to organize their junk into smaller boxes. It takes up less space, but it's all still in the house.
Right.
But L1 regularization walks into the house, picks up a specific weight, and asks, does this neural pathway strictly spark joy? Does it significantly lower the error? And if the answer is no, L1 throws it directly in the trash, it zeroes it out entirely. It forces the network to be an absolute minimalist.
That is a highly accurate and very entertaining analogy. And what makes this specific paper so interesting is that the researchers go a step further than standard practice. Usually when people apply L1 regularization, they apply one global penalty, a single parameter called lambda, to the entire network equally. But this paper proves that applying different regularization parameters, tuning different lambda values for different layers of the network, produces vastly superior results.
Why does treating layers differently matter?
Because different layers of a deep network are learning fundamentally different things. In an image recognition model, the very first layer is usually just learning to detect basic geometric edges, contrasting shadows, and raw colors. It needs a certain number of weights to do that. But the final layer is combining all those abstract concepts to decide if it's looking at a golden retriever or a school bus.
They operate on entirely different scales of complexity.
By manually tuning the lambda penalty layer by layer, the researchers achieved much higher levels of sparsity, deleting more weights without destroying the network's overall accuracy.
Keeping with the analogy, it's like having a different Marie Kondo for your kitchen versus your garage. You need completely different rules for what constitutes clutter, depending on the function of the space.
Precisely. Now, regularization is crucial, but it's not the only way we keep these deep models stable. The CMU homework also heavily features batch normalization. As data flows forward through a deep network, multiplying by weights layer after layer, the scale of the numbers can shift wildly. The output of layer 2 might be between 0 and 1, but by layer 10, the numbers might be swinging wildly between -50 and +500.
That sounds chaotic.
It is. This is called internal covariate shift, and it makes the gradient descent optimizer thrash around violently because the landscape keeps shifting under its feet.
So batch norm fixes that.
Yes. Batch norm steps in at every layer, takes the batch of numbers, and mathematically forces them to recenter around 0 with a standard deviation of 1. It acts like a pacemaker, keeping the flow of numbers uniform and controlled. It stabilizes the landscape, allowing the optimizer to use much larger learning rates and converge vastly faster.
We've spent the last 40 minutes discussing incredibly high-level abstract mathematics, Laplace priors, multidimensional Jacobians, covariate shift. It can start to feel very detached from reality. But I want to ground this deep dive in the actual frustrating day-to-day reality of writing this code.
Oh, please do.
In the stack of sources we reviewed, there was a link to the online discussion forums for the Dive into Deep Learning textbook. And I found a thread there that is just so profoundly, painfully relatable to anyone who has ever tried to code this stuff.
Ah, yes. The infamous forum thread on the softmax implementation in Chapter 3.
Yes. A user named Machine Gurning posts a desperate plea for help. They have copied the textbook's Python code perfectly, word for word, into their VS Code editor on their local machine. The code runs silently. There are no Python errors, no stack traces. But the visual graphs, the plots that are supposed to show the loss going down, don't appear. Nothing plots. They're asking the void if the visualizer only works in a specific Jupyter Notebook environment.
It is the quintessential developer experience. The calculus is flawless, the backpropagation is working, but the software environment utterly betrays you over a plotting issue.
Exactly. And the best part is, 4 years later, in May of 2025, another user named Skixer2 finally replies. They encountered the exact same infuriating problem, and they figured out the hack. To get the matplotlib visualization figure to actually update and show the training progress dynamically in a regular IDE, they had to dive into the background utility code of the textbook and manually inject 2 lines of code, d2l.plt.pos 0.01.
It is a perfect, humbling reminder. We can sit in a studio and theorize about the infinite dimensions of the loss surface or the elegance of the chain rule, but at the end of the day, somewhere right now, a developer is sitting at a keyboard at 2 a.m. fighting with an open-source plotting library, just trying to see a simple line graph of whether their loss went down. Machine learning is high-level mathematics, absolutely, but it is equally a gritty, trench warfare software engineering discipline.
It really is. The glorious road to artificial general intelligence is paved with missing plt.show commands and unresolved library dependencies.
It keeps us grounded.
Okay. We have reached the final major concept of our deep dive. And I have to admit, when I was reading the source material for this final part, it genuinely broke my brain because it contradicts almost everything we just established.
You are referring to the double descent phenomenon from the paper published in the Proceedings of the National Academy of Sciences.
Yes. Because we just spent section 4 talking about how terrifying overfitting is. We talked about L1 regularization, keeping models small, stopping them from memorizing the noise, and feeling zero training error like the plague. We established that as the absolute law of data science. And then this PNAS paper comes along and basically says, hey, what if we just ignore all of that advice? What if, instead of pruning the model, we made it massively, ridiculously, unfathomably huge?
To understand why this paper sent such a shockwave through the academic community, we have to revisit the classical sacred text of statistics, the bias-variance trade-off. For the last 40 years, every single statistics and machine learning textbook has taught the exact same principle illustrated by a U-shaped curve.
Right, the classic U-curve. Let's trace it for the listener. Yeah. Imagine a graph where the horizontal axis is model complexity, how many parameters it has, and the vertical axis is the error. On the far left side of the graph, your model is too simple. It has low capacity. It has what statisticians call high bias.
Exactly.
It is underfitting. It's like trying to predict house prices using only the color of the front door. The model is too dumb to learn the pattern. The training error is high. The test error on new data is high. It's just a bad model.
Correct. So to fix that, you increase the model's capacity, you give it more parameters, more features, you add square footage and zip code. As you move to the right on the graph, the model gets smarter, the training error goes down, and crucially, the test error goes down as well. You reach the bottom of the U-curve. You have found the sweet spot, the perfect balance.
But then, according to the classical theory, if you keep moving, right, if you keep making the model bigger, adding more and more parameters, you enter the danger zone, high variance. The model has too much capacity, it starts overfitting, it starts memorizing the random noise, your training error drops to 0 because it memorized the practice test, but your test error shoots up into the stratosphere because it can't generalize. The right side of the U-curve goes sharply up.
That was the ironclad law. A model with 0 training error is overfit and will generalize poorly. You must stop at the sweet spot. You must regularize. But then empirical practitioners of modern deep learning came along and completely flagrantly broke the law.
Here's where it gets really interesting.
Engineers at places like Google and OpenAI were building neural networks with millions and then billions of parameters. They were building models with vastly more parameters than they had data points. And they were explicitly training them to perfectly interpolate the data, meaning they ran the optimizer until the training error was absolute 0. According to the classical U-curve, these models should have been absolute garbage when tested on new data. The test error should have been astronomical.
But they weren't. They were setting world records in accuracy. The classical theory said they should fail, but the empirical reality was that they were achieving state-of-the-art performance. It was a massive mathematical paradox that troubled theorists for years. The researchers in this PNAS paper, Belkin and his colleagues, finally reconciled this paradox. They discovered the double descent curve.
Double descent, 2 drops.
Explain this to me, because when I first read it, it felt like statistical witchcraft.
It is essentially a continuation of the graph we thought we understood. If you look at the classical U-curve, as capacity increases, test error goes down, hits the sweet spot, and then goes up as you overfit. The absolute peak of that overfitting disaster, the highest test error, happens exactly at what they call the interpolation threshold. This is the exact mathematical moment when the model has just enough parameters to forcefully bend its regression line to touch every single training point.
Okay, so at the interpolation threshold, the model is maximally overfit. It's a disaster.
Yes, but the paradigm shift is what happens if you don't stop there. If you push bravely past the threshold and you make the model even larger, what we call the massively overparameterized regime, the test error doesn't stay high. It doesn't keep going up. It starts to drop again. It descends a second time. And very often it drops lower than the original sweet spot from the classical regime.
Wait, I just want to make sure I'm hearing you correctly.
Yeah.
Are you saying that everything we teach in Statistics 101 about the existential danger of perfect memorization is actually reversed, provided the model is just ridiculously big enough?
Effectively, yes. In the modern deep learning regime, bigger is almost universally better, even if it leads to perfect memorization of the training set.
But how? Mathematically, how is that possible? If a model has 1 billion parameters to fit 50,000 images, it has way too much freedom. It can memorize those 50,000 images in 1 trillion different ways. Why doesn't it just become a chaotic mess of noise? Why does a massively overparameterized model generalize to new data so well?
It comes down to a mathematical form of Occam's razor, combined with the implicit hidden biases of the optimization algorithms we use, specifically stochastic gradient descent.
Break that down for me. I need a visual.
Think about being exactly at the interpolation threshold. You have exactly enough parameters to fit the data points. There is usually only one very specific, highly jagged, complex mathematical function that can perfectly hit every single point. The model is forced to contort itself into a highly erratic, tense shape just to memorize the noise. Because that shape is so jagged and erratic, when you feed it a new test point that falls between the training data, the prediction is wildly off. It generalizes terribly.
Okay, that makes sense. It's like forcing a single, short piece of string to touch 100 random pegs on a board. You have to pull it tight, and it's going to zigzag wildly all over the place.
Exactly. But when you move past the threshold into the massively overparameterized regime, you aren't just giving the model one short piece of string, you are giving it an infinite ocean of string. Because there are exponentially more parameters than data points, there are infinitely many different mathematical functions that can perfectly interpolate the training data.
And some of those infinite functions are going to be wild, erratic zigzags, sure. but some of them are going to be smooth.
Precisely. And this is the magic of the optimizer. Algorithms like stochastic gradient descent inherently favor the smoothest or simplest function. When SGD navigates that infinite dimensional space, it possesses an implicit bias. It naturally gravitates toward the solution with what we call the minimum norm. Out of all the infinite ways to perfectly memorize the data, the optimizer naturally finds the simplest, most elegant, flattest path that connects the points.
Wow. So it actually uses the massive excess capacity not to memorize the chaotic noise, but to find a smoother, simpler underlying truth that it literally couldn't see when it was constrained by a small number of parameters.
Yes. The PNAS paper mentions the ImageNet dataset, a famous benchmark with over 1 million images. To reach this interpolating regime and trigger double descent, a neural network might need 10 to the ninth power a billion parameters. When it has that unbelievable amount of mathematical freedom, the simplest minimum norm solution it settles on generalizes incredibly well to new, unseen photographs.
And the paper mentions another massive benefit to having a billion parameters, right? Something about the optimization landscape itself.
Yes, and it ties perfectly back to our earlier discussion about getting stuck in craters or local minima on the lost surface. It turns out when you make a model massively over-parameterized, you add so many dimensions to the mathematical landscape that the craters essentially disappear.
Wait, how does adding dimensions physically remove a ditch?
Imagine a ditch in standard 3D space, like a soup bowl. If you are a marble in the bowl, you are trapped. Every direction, north, south, east, west, goes up the side of the bowl. But what if you suddenly add a fourth spatial dimension? There is now an entirely new, invisible direction you can step into. And in that new dimension, the terrain might be entirely flat. You can just walk horizontally right out of the 3D bowl.
Oh, that's brilliant.
In a billion parameter space, you have a billion dimensions. It is mathematically highly improbable, almost impossible, to be trapped in a local minimum where every single one of those billion directions goes strictly uphill. There is almost always at least one dimension that allows you to escape downwards. Because of this, SGD easily finds global minima. The landscape, while unimaginably complex, is essentially free of dead-end traps.
That is absolutely mind-blowing. It perfectly bridges the gap. It completely unites the classical statistical theory we relied on for decades with the crazy, rule-breaking empirical success of modern deep learning. We just had to zoom out on the graph. We had to push through the pain of the interpolation threshold to see the second half of the curve.
It really is a triumph of theoretical computer science finally catching up to the brute force practice of the software engineers.
Okay, let's take a collective breath and zoom out ourselves. We have covered an immense amount of intellectual ground today, tracing the evolution of how a machine actually learns. We started with the humble, simple beginnings of trying to draw a line of best fit through data points, predicting a continuous number using regression.
We saw how the statistical concept of maximum likelihood translates practically into the smooth bowl of mean squared error, and we debated the trade-offs of using mean absolute error's sharp V-shape to ignore massive outliers.
Then we leveled up to categorization. We saw how logistic regression uses the sigmoid function to squish outputs into manageable probabilities, and how softmax bakes those probabilities into a competitive pie. We explored the genius of using negative log likelihood to compress the math and prevent computer memory from crashing via underflow.
We strapped on our hiking boots and navigated the incomprehensible, multidimensional mountain range of the lost surface. We used Taylor series approximations to find the slope, Jacobians to isolate the variables, and trace the reverse cascade of accountability through backpropagation and the chain rule, while dodging craters using the physical momentum of SGD.
We brought in our Marie Kondo analogy to ruthlessly tidy up our network with L1 regularization and Laplace priors. And finally, we just threw the classical statistical rulebook entirely out the window and embraced the reality-bending paradigm of double descent, where making a model impossibly dangerously huge actually forces it to become simpler, smoother, and vastly better at generalizing.
It is a beautiful, complex trajectory of how human understanding of artificial learning has evolved over the last few decades.
It really is. And before we go, I want to leave you, our listener, with a final, slightly more philosophical thought to mull over. We just firmly established that artificial neural networks become remarkably better at generalizing, at understanding the world, precisely when they are massively over-parameterized. When they are given 1 billion parameters, way more than they strictly need, and allowed to perfectly memorize their training data, they use that sheer volume of excess capacity to naturally find the simplest, smoothest path through a sea of complexity.
They naturally seek the minimum norm solution.
Right, so here's the thought I want you to take with you. Could human intuition work in the exact same way? We often think of wisdom as the ability to filter out the noise. But maybe, just maybe, do we require a massive, overwhelming overflow of life experiences, random facts, specific memories, and chaotic daily data inputs? Not because we need to remember all of them perfectly forever, but because having an over-parameterized human brain is the only way our minds can eventually distill the simplest, most fundamental, smooth truths about how the world actually works. Are our inexplicable gut feelings and sudden moments of clarity just the human biological version of double descent?
That is a profound parallel to draw. If our brains are the ultimate, original, overparameterized networks, then perhaps our wisdom is just the simplest mathematical function that perfectly fits a lifetime of chaotic interpolation.
I love that. Well, thank you for joining us on this incredibly deep, exhausting, but exhilarating dive into the math, the code, and the philosophy of machine learning. Whether you are currently sweating through building an MLP from scratch in raw NumPy, or you're just trying to figure out why your matplotlib loss curve won't render in VS Code, keep experimenting. Keep exploring the mountain range. We'll see you on the next one.